Okay, so this uniformly distributed mass rod is displaced a small angle and begins to swing back and forth. So you can even imagine like something like my marker, you know, displace a small angle and just begins swinging back and forth. What is a period of oscillation? So, you know, it's summer, so I'm sure the first thing you want to be doing is physics. Go ahead, give this a go on your own, and maybe like maybe you did give it a go on your own. I think maybe the first thing you might be, you know, tempted to do is, well, hey, this is kind of like a pendulum. I might as well try T equals 2 pi square root L over G. And that wouldn't work, right? I mean, let's think about it here. The pendulums that we've been working with before in the past were just there's just some massless string, and then there was just a bob that had all the mass concentrated there. You can imagine that, hey, that has a much higher rotational inertia about this point, right? Because all the mass is concentrated here. This rod has it uniformly distributed. Maybe the period, right? Maybe the angular acceleration will be affected by the torque, right? It also has, like, you know, in the center, there's less torque, but there's, you know, if you think about the L squared and all that, there's just less rotational inertia. Maybe the angular acceleration is affected, and it's not going to be like the same period. It's not going to be exactly the same as like a pendulum, a simple pendulum that we've been working for. This is a physical pendulum, and you got to approach it in a bit of a different way. And by a bit of a different way, like, you're not just going to be plugging in L and G and then getting the answer. So let's just start from the beginning. We know that the angular acceleration is equal to torque net over rotational inertia, right? This is Newton's second law for rotation. So the let's just actually start substituting in values. Like, torque net is just, it's the torque by gravity. So if we think about the center of mass, it's going to be kind of in the halfway point of the rod. So the torque is Fg. That's the only force that's causing a torque. Mg sine theta, right? Because it's going to be the perpendicular component of that force, the lever arm. Mg sine theta L over 2. That's the distance that the force is acting from. So this is literally just force times lever arm, right? I'm just torque net over rotational inertia. Well, if you don't know it off the top of your head, you can integrate it, which is a lot of fun. It is 1/3 ml squared. I don't know if they give you that on the test for physics C, but whatever. Boom, there you go. So a couple things off the bat. Hey, the mass cancels out. So that's something that, you know, is a reoccurring thing in physics. And this L gets away, and then this loses its squared, right? So L over L squared. And we can clean this up. We have a 1/3 here with a half there. You can really get alpha is going to equal, okay, 3g sine theta over 2L, right? If you just do the fraction math, this goes on the bottom, this goes on the top. So now we're here, and this is kind of not fun. Like, what do we do here? How do we figure out the period? Well, we know that the rod has displaced a small angle. So the angular acceleration is right now proportional to sine theta, right? Which, that's not a lot of fun, because sine theta is a really weird graph. But if it's displaced a small angle, sine theta is basically theta. Like, if you go into your calculator and you plug in like sine 0, it's 0. If you plug in sine like sine 0.1, it'll be around 0.1. Heck, if you even do sine pi over 6, that's pretty close to 1/2, 0.5. You can even just type in pi over 6. No, sine pi over 6 is exactly 1/2. Pi over 6 is pretty close to 1/2. When you have a small angle, sine theta is basically theta. It's an approximation, small angle approximation. So this is pretty helpful, because we know that sine theta is going to be a cosine. Like, if you did theta over time, it's a cosine graph, right? The theta is going to start from a maximum, reach a minimum, maximum, and it's going to be a cosine graph. So if you imagine, if theta is cosine, imagine doing sine cosine t, right? Where, you know, this is like, you know, this is going to be a cosine omega t. So if you imagine plugging that back into here and then solving, it's going to be a whole nightmare. By approximating, just makes our life a lot easier. And then from there, it's just a matter of, hey, I know alpha, if theta is cosine, then alpha is going to be you know, if you take the second derivative, this is d, if you do d squared theta over, what's the word? dt squared, right. And then, you know, you can start thinking, well, if 3ga, and then we can put the negatives as well. I forgot to do that. It's restoring force, or restoring torque. 3ga cosine omega t over 2l, and then we got to do the second derivative, and you can figure it out. It's negative a omega squared cosine omega t. So if that part was like, oh, I don't know where that came from, the omega squared, it's just the second derivative. And then yeah, you just start canceling things out. This negative can go away. This a can go away. This whole cosine omega t, if you're thinking, what the heck is that doing here? It's gone. And now you're really just left with omega squared equals 3g over 2l. Maybe this is starting to look familiar. When you start taking, oh, this is a real familiar, square root. We have omega is equal to 3g, square root 3g over 2l. And omega, for our angular frequency, that's the same as 2 pi over t. If you're wondering, why is omega doing here? What is omega doing here? T, right, after at cosine 2 pi, it starts again. So in order to get the period 2 pi over t, to get 2 pi, you would need 2 pi over t as omega. And then this is going to equal root 3g over L, 2L, I should say. And by here, you could probably figure out the rest. We're solving for period now. So 2 pi over t. I'm just going to solve for it. You get t. If you multiply this here, divide by the reciprocal, you get t is equal to 2 pi square root 2L. wait a second. 2L over 3g. That seems right. Let me just make sure I didn't make any mistakes with my algebra. Yeah, I hope this is right. There you go. This is your kind of answer. You just plug in now L and G, and it's in kind of the same form as like this equation, right? But now there's that 2L over 3G. So you can imagine, if we think about proportional reasoning, this is 2/3. So square root 2/3. You can plug in your answer. So 2 times pi times the length is 1.6. So square root 2 times 1.6 divided by, and then make sure you have your parentheses. 2 times 1.6 divided by 3 times 9.8. You should get 2.07. Now, if you did that same thing and plugged it into there, right, instead of having the 2 over 3 kind of thing going on, you would have gotten 2.53. So that's like a half a second difference. I know, right? What a crazy difference. It's night and day. But hopefully the point was showing you that rotational inertia and the shape of your pendulum, your physical pendulum, does impact your period. It's not, and I hope, even if the math didn't make sense, I hope that kind of makes sense, right? You have a different rotational inertia. Your angular motion is going to be different. Your period is going to be different. So, yeah, there you go.